Okay, welcome back. We're in section 6.2, which is applications of the exponential functions. We're going to see some of these exponential functions in action. They are quite common. You'll see them in finance, you'll see them in biological modeling. They're quite a common thing. So let's take a look at a couple of applications where they show up. The first one is in finance, and we're given this formula, the annually compounded interest formula. Okay, so if you go to a bank, most banks don't do annual compounding, but that's okay, we have to start somewhere. But if you go to a bank, you say, here's a bunch of money, and they say, well, we're going to give you interest, and we'll compound that annually. What that means is at the end of every year, they'll examine it, do the calculation, put that money in, and then essentially start that clock over, and at the end of the next year, they'll do the same thing. They'll go in, examine it, do a calculation, throw in your money, right? So if you wanted to see how much money was going to be in your account after however many years, then you would use this formula. Now as a function, I'm calling this function a to represent the amount, but it's a function of t, so this is a function where the variable is t, so this whole thing just means the amount. Now there's a couple of things in here, right? There's the first, we call this the amount, that's the amount that you have, the amount in the account. Sounds like a Dr. Seuss thing. After t number of years. Right? That's what a of t means. Right? This p is the principal. It's the amount that you started with. Right? When you go in there and say, here's my money, dump it on the table. It's not how stuff works, but yeah, we're pretending, right? But you go in there, the amount that you put into the account from the very start. That's the very beginning amount that you say, here you go, put this into an account for me. This R is the annual interest rate. And then T, of course, is the number of years. But that's our formula. A of t is the principal multiplied by the sum of 1 and the rate, and then that raised to the number of years. Right? So let's see this in action. And these are primarily calculator problems because if you get something raised, if you want to find something to the 10th power, to do that by hand, you would have to take this kind of ugly decimal, multiply it by itself, and again and again and again and again. So in your calculators, there's all sorts of different kinds of calculators. You'll need to figure out how to raise a number to a power in that calculator. Normally, if we were in class, I would have you all break out your calculators and I'd walk around and show you this, but you may have to YouTube your specific calculator and see how to do an exponent in your calculator. But let's start here. Let's just say I deposit $15,000 into an account. Earning 4% interest, and that interest is compounded yearly. That right there, you'll see that in the questions. That's your cue to use the equation that I just wrote down, or the formula that I wrote down. And then the question is, how much is in the account after, let's say I'm going to leave it there for 12 years. So I use that formula. I have it, I want to use it. Here it is again, it's A of t is equal to the P principal multiplied by 1 plus R raised to that t. And all I really have to do is recognize what P, R, and T are. So P, the principal, it's the amount that I put into the account, is $15,000, and I realize I wrote that above the screen, but this is P, is $15,000. R is the 4%, so this 4% means that R as a decimal is 0.04. I want that as a decimal, a pure number, get rid of that percent. And then T is 12. So all I have to do is say A, the amount after, and I can write it as this, the amount after 12 years is equal to the principal, which is 15,000, multiplied by 1 plus 0.04, all raised to the 12. Right? Now, I would do a lot of this by hand to start off, just to make sure that I don't throw in a huge thing into my calculator and mess it up. So I'm going to simplify this 1 plus 0.04. One plus 0.04 is just 1.04. And then to start, again, some calculators you can put this whole thing in, but if you try on some other calculators, it'll mess it all up and, you know, get you the wrong answer. So in your calculator, try this. If you get the same number as me, great. Either we both screwed up or we both did it right. But I would start by taking 1.04, raising it to the 12, getting that value, and then multiplying that result by 15,000, right? So when I do that, I get taking me a second here, sorry, 1.04 raised to the 12 is $1.601032218, and it goes on for quite a ways, right? In fact, there's going to be 24 decimals, right? 24 digits after the decimal, right? And it's impossible, your calculator is going to cut this off at some point and just say you don't need to know anything past that. But if you keep this number, instead of rewriting it and then multiplying it by 15,000, just take this number that's already in there, just times 15,000. On most calculators, it'll just take whatever that number is stored in there and then multiply it by 15,000. And so if I do that, then I get $24,015 and 48 cents. And I'm going to round it at my 48 cents. The next digit after that's a 3. We're talking about money. If you went into your bank and said, hey, where's that third of a penny, they're going to laugh at you. They round everything to the penny, so there we have it. After 12 years, we're going to be at $24,015.48. Good. I might also find this calculation present when I take out a loan. I take out a loan of $12,000 at an annually compounded rate of, let's say it's a loan, so I'm probably going to get a much higher interest rate. Let's call it 8%. For 4 years. Right? First off, I realize if you've ever taken a finance class, you're never going to find this loan out there. Nobody's going to say, here's some money, pay me back in 4 years, but we're starting at the base level here, right? So we're pretending this might happen. But the question is, how much do I owe after those 4 years? Okay. So it's the same formula, it's just the amount, right? This is essentially, this guy that loaned me this money is depositing money at a very good interest rate to himself, right? And so the amount that he's earning is the principal amount multiplied by that 1 plus r and then raised to the t. The principal amount is $12,000, the rate is 8%, the t is 4 years, and so the amount that I owe him after these 4 years is $12,000 multiplied by 1 plus 0.08. So I'm just going to cheat and simplify that right from the get-go. 1.08 raised to the 4. So again, I'll write this down, 1.08 raised to the 4. Gives me something around, this would be 12,000 still, multiplied by 1.36, 048896. And if you don't have a calculator, you don't have to go out and buy one. You can go to mathway.com, I think is what it's called. And you can do your calculations in there. The nice thing about mathway.com, and I'm going to look it up to make sure I'm not lying to you about the address, is that you can actually plug this whole thing in and it'll know to take this to the power and then multiply it. It'll know the order of operations. But if I then do the multiplication of this number by 12,000, this becomes 16,325 and 80, I'm going to round this up to 87 cents. And that's how much I owe this loan shark after 4 years. Alright, so I'm looking here, Mathway, and it just looks like this. Right? It's just a basic calculator, but you can throw in just about anything in there, and it'll do those calculations for you, right? Alright, let's move on to our next example here. One of the very powerful tools in finance is the time value of money. As long as you can beat inflation rates, you can hold money into accounts for as long as you can, that's going to become more and more valuable to you. So an example of that, let's say one of the examples in the book says, Jen receives an inheritance. Of $50,000. She wants to leave it in the account earning 6% interest annually compounded. And she wants to leave it in until she retires in 25 years. Right? So imagine this is you. If you get an inheritance of $50,000, you could just go blow it on a Lexus, or probably not even a Lexus anymore, a Hyundai. I don't know. Cars are ridiculous. But you could blow it pretty quick, pretty easy. It's easy to blow $50,000 in one day. It's not smart to, but it's easy. If we instead throw it in that account, earning 6% annually compounded for 25 years, how much do we have at the end, right? Well, then we're asking the amount after 25 years, which is equal to the principal, which is that 50,000, multiplied by, we're earning 6%, so the 1 plus R becomes 1.06, and then we're raising that to the 25. And again, that's where the power is in the power. That's terrible, but whatever. That's where the magnitude of this number is going to become great, is with that 25. So if I calculate this, and I'm going to skip the the tedium here, I'll just throw it straight in. This becomes 50,000 times 1.06 raised to the 25. This 50,000 just got turned into 214,000. 593. I guess I could have cheated because the number I think is in the example. And 54 cents. They rounded it to the nearest dollar in the example, but this is what she has. So you can have $50,000 today, buy a car, or you can have $214,000 in 25 years and, live in Europe for a couple of years. I don't know. There we go. Okay. Now again, I mentioned this, but most banks don't do annually compounded anything because money doesn't stay in accounts for all that long anymore. They get shuffled around here and there. But most of them will do monthly compounding. And some of them do weekly compounding, some accounts do quarterly compounding. They can compound however many times you want per year. And so the general formula for compounded interest is just a little bit different. It's not a lot different. It's the amount after however many years, so T is still in years, is equal to P multiplied by 1 plus, and this is where the change is instead of the rate itself, it's the rate divided by however many times you compound every year. And then still raised to the number of compounds, which is n times t, right? So again, n now is, everything else is the same. It's still r is the annual compounded rate, but n is the number of compounds that you do in a year. So if you compound monthly, n is 12. If you're compounding weekly, n is 52. If you're compounding quarterly, n is 4, right? So you have to figure out your n based on the problem. Let's look at a problem. Let's say I deposit $40,000 into an account earning, let's say I'm lucky enough to get an 8% interest rate. If you look at the bank, like if you have a checking account, they're legally required to give you interest So most checking accounts nowadays give you like 0.1% interest. You'd have to go outside of your checking accounts to find something this good, and most things that are around 8% are stocks, and those are sometimes up, sometimes down, so. But we're not talking about finance, we're talking about math, so let's continue on here. 8% interest, how much is in the account? Oh, compounded, sorry. Compounded, let's say monthly. And so I want to find, let's say, two things. The amount that's in the account after, let's say, 3 years. And let's find the amount that's in the account, if I were able to leave that for 30 years, how much would I have, okay? So let's do the 3 years first. The amount in the account of 3 years is the principal, so 40,000. In fact, what I'm going to do, I'm going to scoot this over here. We'll see them side by side. A of 3 is equal to $40,000 multiplied by 1 plus, this is my 0.08, right? That's the R divided by, since we're compounding monthly, it's divided by 12, and then this is raised to the 12 multiplied by 3, right? I said we're going to see these side by side, but there's no way I'm going to be able to fit the other one over here, so I lied. But if I start here, I take the 0.08 divided by 12. Oops. So that is a repeating number, so I've got this 40,000 multiplied by 1 plus, this ends up being 0.00666 forever onwards. Still raised to the, and I can take this, 12 times 3 is 36, right? So this is then that 40,000. 1 plus that is just 1.00666 forevers to the 36. So this 1.0666 forevers raised to the 36 gives me somewhere in the neighborhood of 1 point, nope, not 1, 10, that can't be right, what did I do wrong? Oh, I did something wrong. One point 27023 7, and it goes on, it's forever long, but if I take that and multiply it by 40,000, then I get $50,809. And some change, 48 cents. Not bad for 3 years, dump it into account, $10,000 increase over 3 years. Not bad. Right? If I want to do it for 30 years though, I'm actually going to leave most of these numbers here, because what changes is only this 3 right here. This 3 is now a 30 if I want to find the amount after 30 years, right? And you can see then 12 times 3, which was 36, well 12 times 30 is now 360, right? So this number is going to change. Now that I've taken this 1.0666666 to the 360 now. side here is now the 10.93. $572, and it goes on and on and on. Not terribly important, but when I take that 40,000 multiplied by that, I'm going to end up with north of $400,000. And it is 437, 429. And it looks like it would be rounded to 19 cents. Okay. And then interestingly enough, if after 30 years I was so savvy with money that I was like, hey, I'm just going to dump this onto my kids into their retirement and they have another 25 years, then we'd be looking for A of 55, right? And I can do that as well, right? If I want to just set my kids up for retirement, instead of 30 now, it's 55, let's say. So 12 times 55, which is 660. Right. Changes this number. I'm just gonna skip this step though. It doesn't really matter what that number is so much. But if I take this 1.00666 forever up to the 660 and then multiply it by my 40,000, what do I get? My child gets to retire on $3,210,807 and 20 cents. Right. So again, the time value is a huge theme with these exponentials. But unfortunately, if this is me 55 years later, I probably don't want to give that to my kids. I probably want to buy a yacht and live in the Pacific. All right, let's move on from this one. Let's look at the opposite idea here. Sometimes you buy something and it loses value. Stocks, sometimes, cars, almost all the time. But that is called depreciation. Right? You buy a car, the second you drive into the street, that car is now worth, a good 20% less than you paid for it, right? Which is super. But every year, since you're using this car and it's a mechanical machine, things wear out, it gets worth less and less every year. So this is almost the same well, it is the same formula, except it's just called a couple of different things. Instead of the amount in an account, it's just now called the V of T for the value, but it's still P1 and it's minus R because we're now losing value, and then still raised to the T, right? Okay. So for example, I bought a car for, let's say, $40,000. This car is known to depreciate at 6% annually. And I want to find the value of this car, let's say 10 years later. Right? I want to find the value at 10 years in, what's my value, right? So that is just V of 10 is equal to the principal, right, the amount that I paid for the car, so that's the $40,000. Multiplied by 1 minus 6%, so 0.06, and then raised to the 10 years. So I'm going to erase all of this up here so that I can work this. This then equals 40,000. 1 minus 0.06 is 0.94, and I'm raising that to the 10. So again, depending on your calculator, you might be able to just write 40,000 multiplied by 0.94 raised to the 10, but if your calculator does not allow multiple operations in one line, then you won't be able to do that. But I'm going to skip the steps here, and I get 40,000 multiplied by that 0.94 raised to the 10 gives me 21,544. And I would round this to about 60 cents. Right? I think most of the problems in the book are going to ask you to round to the nearest dollar, because in reality, when you go to the dealership, they're going to try to round you to the lowest $1,000 anyway. So that's our value. And this is not always exact, right? I think Kelley Blue Book does something like this, but there's always that huge dip from the very beginning. You buy the car, drive it off the lot, you lose a huge percentage. And then you might lose on average this percentage, and that's how they calculate those values. But there's other factors like the mileage that you drive, the location that the car is. For example, if you're in Montana, Idaho, Utah, harsh weather in the winter, salt on the roads all the time, as opposed to if you're in Las Vegas and it's 8 million degrees all summer, those kind of things. But there's our car. All right, let's do one more of these perhaps. Let's say a machine is known to depreciate at 4% annually. A factory buys one. For $700,000. It's a very big machine. Find the value of the machine after 20 years. So then our value after 20 years is equal to the principal, which is 700,000, multiplied by 1 minus this 0.04, and we're looking for 20 years, so raised to the 20, or 700,000, multiplied by 0.96, raised to the 20, and I get 700,000 times 0.96 raised to the 20, 309,000 and 401 and some change, 70 cents. But again, usually nobody cares about the cents. Okay. But if your questions do ask you to round to the cent, right, make sure that you know how to round. Some of them might ask you to round to the nearest dollar. If they did, this would be 309,402 because it's next digit is higher than 5. All right, thank you, and I will see you guys for the next one.